Welcome to the deep dive. Today, we're tackling a truly massive question. What's keeping the universe alive?
It really is fundamental, isn't it?
Absolutely. We're going on this incredible journey looking at the forces, the structures, the deep mysteries that shape everything, right from the universe's first moments to its far off future.
And we're using a fascinating guide for this.
Yeah, A Dragon's Cosmic Chronicle by Zoran. It offers this really ancient, almost mythical perspective, but grounded in cosmic truths. Helps cut through the noise.
Definitely. So our mission today really is to pull out the key insights, the surprising bits from Zoran's Chronicle. Think of it as your essential guide to the universe's workings.
A shortcut, maybe.
Maybe. We'll see how it all connects from creation to, well, whatever comes at the end. Hopefully it gives you a clearer picture of the whole grand story.
Okay, let's dive in, the very, very beginning. The universe's first breath, as Zoran puts it.
That's almost impossible to picture.
Right. Imagine everything, absolutely everything squeezed into a point smaller than
Yeah.
smaller than anything you can imagine.
Infinitesimally small.
And then, bam, faster than thought, it just exploded outwards. Science calls it cosmic inflation.
And explosion doesn't quite capture it. It was an exponential expansion of space itself.
Yeah, the scale is just nuts. We're talking, what, a tiny fraction of a second? Like a trillionth of a second, maybe?
Something like that, from subatomic size to, well, maybe grapefruit-sized initially, then vastly larger, almost instantaneously.
Wow. So why was this inflation so important?
Well, that's the crucial part. It basically set the stage. See, cosmologists had these two big puzzles. The horizon problem, like how did opposite sides of the universe end up at the same temperature if they never had time to exchange heat?
Okay. Yeah, that seems weird.
And the flatness problem. Why is the universe geometrically flat like a sheet of paper instead of curved like a ball or a saddle?
It seems
Too
definitely.
perfect.
So inflation fixed that.
Exactly. By stretching space so incredibly fast, it smoothed everything out. Ironed out the wrinkles, you could say. Made it uniform and flat. It's why the large-scale structure looks the way it does today.
Okay, so after that initial, hyper expansion, what was the universe like?
Not cold and empty, that's for sure. It was this incredibly hot, dense soup. Pure energy, basically.
A
A
soup.
primordial soup, yeah.
Yeah.
Zoran calls it teeming with fundamental particles.
Mhm.
You've got quarks, leptons, like electrons, photons, the light particles just zipping around everywhere.
So not atoms yet.
Oh no, way too hot for atoms. Energy and matter were just constantly swapping places. E=mc² in full effect.
Right, Einstein's famous equation.
Particles popping into existence from energy, smashing into each other, turning back into energy.
Mhm.
A real swirling maelstrom. This was the crucible where the basic ingredients got cooked up.
So the universe keeps expanding and it starts to cool down a bit.
Right. And as it cools, things start to settle. Between, say, a few minutes and maybe 20 minutes after the Big Bang, it cooled enough for quarks to stick together.
Forming.
Protons and neutrons. And then those stuck together to form the very first atomic nuclei.
Which were?
Mostly hydrogen and helium, the simplest ones. This whole process is nucleosynthesis.
And they're still the most common elements, right?
By far, about 14 hydrogen atoms for every one helium atom, roughly. That ratio is like a fossil record from those first few minutes.
But why only hydrogen and helium? Why not heavier stuff like carbon or oxygen?
Good question. It comes back to the cooling. The universe expanded and cooled too fast, just zipped right past the temperature window needed to fuse heavier elements.
Okay. So this hydrogen and helium just hung around.
Yep. Became the raw fuel for the very first stars, which wouldn't form for millions of years yet.
Okay, fast forward a bit. There's this thing called the cosmic microwave background, the CMB. What's that about?
Right, the CMB. Think of it as the universe's baby picture. Around 380,000 years after the Big Bang, the universe cooled down enough, maybe 3,000 degrees Kelvin.
Still pretty hot.
Oh yeah, but cool enough for electrons to finally latch onto those hydrogen and helium nuclei, forming stable, neutral atoms for the first time.
And why was that such a big deal?
Because suddenly, light could travel freely.
Yeah.
Before that, the universe was like a thick fog. Photons just kept bumping into free electrons.
So it became transparent.
Exactly. And that light, released all at once, has been traveling ever since. As the universe expanded, the light waves got stretched out, cooled down.
Into microwaves.
Precisely. That's the CMB. We detect it today as this faint, uniform glow coming from all directions, about 2.7 degrees above absolute zero. It's like the ultimate proof of the Big Bang.
But it's not perfectly uniform, is it? There are tiny temperature differences.
That's the key. Those tiny fluctuations, the primordial ripples, are incredibly important. They were the seeds, the slightly denser spots that gravity could grab onto later.
To form galaxies and stuff.
Everything. Galaxies, clusters, the whole cosmic web, it all grew from those tiny seeds imprinted on the CMB. It's basically the blueprint for the cosmos.
So if you were there like an electron back then, just bouncing around.
For 380,000 years.
Yeah.
Then suddenly, things cool, you join an atom, and whoosh, light floods the universe.
That's a nice way to put it. That first light, the CMB, is still whispering those ancient secrets to us.
Okay, so we have hydrogen and helium. The universe is transparent,
Mhm.
but still pretty empty and dark, relatively speaking. What lights it up?
Stars, the next great act. They are the cosmic engines, the heartbeats of the universe.
How do they get started?
It starts in these huge, cold clouds of gas and dust floating in space, nebulae. Think of them as cosmic nurseries.
Cold. I thought stars were hot.
They get hot, but they start cold and diffuse. Gravity is the key. It slowly pulls the denser parts of the cloud together.
Just gravity.
Yep, gravity's subtle, relentless pull. Over millions of years, clumps form. They start to spin, shrink, and heat up. That's a protostar.
A baby star.
Basically, yeah. Still gathering material, getting hotter and hotter in the core.
Until the core gets incredibly hot and dense millions of degrees. Then, nuclear fusion kicks in.
Hydrogen fuses into helium.
Exactly. Stellar nucleosynthesis. That releases enormous amounts of energy, light, and heat. That's what makes a star shine. That's the main sequence phase. Our sun is in it now.
And they just keep doing that, fusing hydrogen.
For most of their lives, yes.
Hmm.
But stars are like cosmic alchemists. They don't stop there, especially bigger ones.
What do you mean?
Well, once a massive star runs out of hydrogen in its core, it starts fusing helium into carbon, then carbon into oxygen, and so on, all the way up to iron.
Wow. Creating heavier elements inside the star.
Right. Each step needs more heat, more pressure, so you get layers like an onion fusing different elements. They're literally building the building blocks of planets and us.
But stars don't live forever. They have life cycles, right?
They do. After the main sequence, things change. A star like our sun will swell up into a red giant.
And bigger stars.
Become red supergiants. Then, depending on the mass, they meet different ends. Sun-like stars shed their outer layers, leaving behind a hot, dense core called a white dwarf. Just a cooling ember, basically.
Okay, what about the really big ones?
They go out with a bang. Stars maybe 8 to 30 times the sun's mass collapse catastrophically. The core becomes an incredibly dense neutron star.
Neutron star, how dense.
Get this. A teaspoonful would weigh billions of tons on Earth. Insanely dense.
Whoa. And the absolute biggest stars.
Bigger than, say, 30 solar masses. Their cores collapse completely. Gravity wins outright. They form black holes. Nothing, not even light, can escape.
Ugh.
Zoran calls them ultimate cosmic recycling centers.
Okay, you said stars fuse elements up to iron. But what about gold, platinum, the really heavy stuff?
For those, you need even more extreme conditions. You need cosmic fireworks.
Fireworks.
Supernovae, the explosive death of massive stars. For a brief time, a supernova can outshine its entire galaxy.
And that's where gold comes from.
That, and another even more energetic event, neutron star mergers. When two of those super dense neutron stars collide, wow.
What happens?
An unbelievable explosion, creating and flinging out the heaviest elements, gold, platinum, uranium, all that stuff. So literally, the gold in your jewelry was forged in a dying star or a neutron star smash-up.
It's incredible. These violent deaths actually seed the universe with the materials for new stars, new planets.
Exactly. It's a cycle. Death and rebirth on a cosmic scale.
Yeah.
You really are made of stardust.
Imagine being like a hydrogen atom, starting in a nebula, getting fused in a star, maybe becoming carbon, then maybe getting blasted out in a supernova.
To eventually become part of a planet or maybe even, part of someone thinking about it billions of years later.
Yeah.
It's quite a journey.
Okay, so we have stars making elements exploding.
Yep.
But they don't just float around randomly, do they? They gather together.
All right, gravity pulls them into enormous structures, galaxies, billions, sometimes trillions of stars all bound together. This is the grand architecture.
How did galaxies first form? Was it just gravity pulling stars together?
Sort of, but it goes back further. Remember those tiny ripples in the CMB?
The seeds.
Those are the starting points. Slightly denser regions of gas, and crucially, dark matter, we'll get to that, started pulling in more material.
They are millions, billions of years.
Exactly. From maybe 200 million to a billion years after the Big Bang, these clouds collapsed, started spinning, fired up the first stars, forming messy, chaotic proto-galaxies.
Autogalaxies, so not like the neat spirals we see now.
Not at all. The early universe was pretty chaotic. These small galaxies smashed into each other, merged, grew bigger. It was a pretty violent cosmic childhood.
And that's how we get different shapes of galaxies.
Largely, yes. The mergers and interactions sculpt them. You get the beautiful spiral galaxies, like our Milky Way, with arms full of gas, dust, and young blue stars. Active places.
Our Milky Way is a spiral.
A Bard spiral, yeah. Then you have elliptical galaxies, more like big, smooth blobs, less gas and dust, mostly older, redder stars, often the result of major mergers.
Okay, spirals and ellipticals. Any others?
Irregular galaxies, no real defined shape, often smaller, maybe messed up by interactions. Lots of chaotic star formation sometimes. The Magellanic Clouds near us are examples. Each type tells a story of its past interactions.
And galaxies themselves cluster together too, right?
Oh yeah, gravity doesn't stop. You get galaxy clusters, hundreds or thousands of galaxies bound together, often filled with superhot gas you can see in X-rays. The Coma cluster is a famous one.
Thousands of galaxies.
Wow.
And even bigger structures.
Yep, superclusters. Clusters of clusters, stretching hundreds of millions, even a billion light years across. They form this vast network. People call it the cosmic web.
A web?
Kind of. Huge filaments made of galaxy clusters and groups connected across space with vast, mostly empty regions called voids in between. Our galaxy is in the local group, which is part of the Virgo supercluster. It's this incredible, vast tapestry.
And sitting at the heart of most big galaxies.
Is usually a monster, a supermassive black hole.
Supermassive.
Yes, yeah.
Millions or billions of times the sun's mass.
That's right. Our Milky Way has one, Sagittarius A, about 4 million solar masses. They seem to be crucial for galaxy evolution.
How so?
Well, when they're feeding on gas and dust, they can become incredibly bright. Active galactic nuclei, or AGN. The brightest are called quasars, mostly seen in the early universe.
And they affect the galaxy around them.
Definitely. The energy blasting out from an AGN can trigger bursts of star formation or sometimes blow away the gas and shut it down. They're like silent conductors of the cosmic orchestra.
Imagine floating above a galaxy cluster, seeing all those different galaxies, then zooming out to see the whole cosmic web.
And knowing there's this immense black hole anchoring the center of almost every large galaxy, it's an awe-inspiring structure.
Okay, we've talked about stars, galaxies, black holes, the visible stuff, but what's holding it all together? What makes it all work?
Now we get to the invisible threads, the fundamental forces, the rules of the game.
Starting with the big one, gravity.
The most familiar, yet maybe the most mysterious. It pulls everything together, shapes the largest structures. It's always attractive, acts over infinite distance, but gets weaker with distance.
And Einstein said it's not really a force, but space-time warping.
Exactly. General relativity. Mass and energy warp the fabric of space-time, and other objects follow those curves, like a bowling ball on a rubber sheet making marbles roll towards it. It's this slow, persistent influence that builds cosmic structure over billions of years.
Okay, force number 2.
The electromagnetic force. This governs anything with electric charge. Opposites attract, likes repel. It's responsible for light, electricity, magnetism.
Chemistry, life.
All of it. It holds electrons in atoms, binds atoms into molecules. It's way, way stronger than gravity at small scales. Think of a fridge magnet holding up a note against Earth's pull. It makes the universe interactive, vibrant, colorful.
Then we get into the really small scale inside the atom's nucleus.
Right. The strong nuclear force. This is the powerhouse. About 100 times stronger than electromagnetism, but only acts over incredibly tiny distances, like the size of a proton.
And its job?
It's the cosmic superglue. It binds quarks together to make protons and neutrons, and then it binds those together to make atomic nuclei stable. Without it, nuclei would fly apart, no elements beyond hydrogen, no stable matter, period.
Wow. Okay, and the last one, the weak force.
The weak nuclear force. Weaker than strong and electromagnetic, yes, but crucial. It's responsible for certain types of radioactive decay. It allows particles to change their identity like a neutron turning into a proton.
And that's important for
stellar fusion, for one. The process that powers the sun involves the weak force changing protons into neutrons. It's also involved in creating some heavy elements in supernovae. It's the universe's subtle transformer, enabling slow changes. Works via heavy messenger particles, W and Z bosons, which is why its range is so incredibly short.
So these forces, plus the particles, that's the standard model.
That's our current best picture, yeah. The standard model of particle physics describes electromagnetism, The strong force, the weak force, and all the fundamental particles, quarks, leptons, force carriers like photons and gluons, the Higgs boson. It's incredibly successful. Predicted particles we later found.
But there's a but, isn't there?
There is. It doesn't include gravity. It's still separate, described by general relativity. And maybe more importantly, it doesn't explain dark matter or dark energy.
So it's not the complete picture.
Not by a long shot. It's a fantastic achievement, but definitely a work in progress.
It's amazing to think you pick up, say, a rock, and all these forces are working inside it. The strong force holding nuclei together, electromagnetism holding atoms together, gravity keeping it in your hand.
Absolutely. It's an invisible dance happening constantly everywhere.
Which brings us nicely to the big unknowns, the things not in the standard model, dark matter and dark energy.
The elephant, or rather the two elephants in the cosmic room, making up, 95% of the universe's total energy density.
95%. And we can't see it.
That's the gist. We started noticing things didn't add up gravitationally. Galaxies were behaving weirdly, as if there was a lot more mass than we could account for just by looking at stars and gas.
So dark matter, matter that doesn't interact with light, but has gravity.
Precisely. Doesn't emit light, doesn't absorb it, doesn't reflect it, just sits there gravitationally. But its presence is undeniable.
How do we know? What's the evidence?
Several lines. A big one is galaxy rotation curves. Stars way out in the spiral arms of galaxies are orbiting much faster than they should if only the visible matter was providing the gravity.
Like they're being held onto by something invisible.
Exactly. Implies a huge invisible halo of dark matter surrounding the visible galaxy, making up maybe 85% of its total mass. It's like invisible dancers swinging their visible partners around really fast.
Okay, what else?
Gravitational lensing. Massive objects warp spacetime, bending light passing by. We see light from distant galaxies being bent way more strongly by galaxy clusters than the visible mass can explain.
So the lensing reveals extra invisible mass.
Yes, dramatically shown in things like the Bullet cluster, where you can literally map the dark matter separately from the hot gas. And the cosmic microwave background, again, the detailed pattern of those tiny temperature fluctuations perfectly matches a universe filled mostly with dark matter, which acted as the gravitational scaffolding for structures to form.
So we're sure it's there, but what is it?
Ah, the million-dollar question. Or maybe trillion-dollar. Not ordinary matter, not protons, neutrons, electrons. Leading candidates are hypothetical particles called WIMPs, weakly interacting massive particles.
WIMPs?
Yeah, massive, but barely interacting with anything except gravity. We have big experiments underground trying to detect the incredibly rare bump of a WIMP hitting an atomic nucleus. Other ideas include axion superlight particles or maybe sterile neutrinos. Old ideas like faint stars or black holes called machos have mostly been ruled out. It's a huge cosmic hunt.
Okay, so that's dark matter, the invisible gravity source. What's dark energy?
Dark energy is. Well, it's almost the opposite. It's some kind of invisible push that's causing the universe's expansion to speed up.
Speed up. I thought gravity would be slowing it down.
Everyone thought that. Until the late 1990s, two teams were studying distant supernovae-specific types called Type Ia, which act like standard candles, meaning we know how bright they should be.
Okay.
They found these distant supernovae were fainter than expected for their distance, which meant they were actually further away than expected.
Meaning the universe had expanded more and faster than we thought.
Exactly. The expansion is accelerating. Something is fighting against gravity on the largest scales and pushing everything apart faster and faster. That something is dark energy.
And this makes up even more the universe than dark matter.
Yep. Current estimates are around 68% dark energy, 27% dark matter, and only about 5% is the ordinary matter that makes up stars, planets, and us.
That's humbling. 95% is unknown stuff.
It really puts things in perspective, doesn't it? A hidden cosmic orchestra conducting most of reality.
So what could dark energy be? Any ideas?
The simplest idea is the cosmological constant, often represented by the Greek letter lambda. It's basically the energy inherent in empty space itself. As space expands, you get more space, so you get more dark energy, leading to a constant accelerating push.
Sounds neat. Is there a catch?
Oh, is there ever? When physicists try to calculate how much this vacuum energy should be based on quantum physics, the number they get is, well, it's catastrophically wrong. It's about 10 to the power of 120 times bigger than what we observe.
120 zeros.
Yeah, it's possibly the worst prediction in the history of physics, called the cosmological constant problem.
So maybe it's not that.
Maybe not. Other ideas include quintessence, a dynamic field that changes over time, Or maybe our understanding of gravity, Einstein's general relativity, needs tweaking on cosmic scales. We just don't know yet.
So imagine you're floating out there between galaxies.
Hmm.
You'd feel the pull of the dark matter in those galaxies, but also this gentle, constant push everywhere from dark energy shoving everything further away.
That's the picture, yeah. Feeling the effects of 95% of reality that operates completely beyond our direct senses. Kind of eerie.
Okay, so we have this universe expanding faster and faster, filled with mysteries. Where does it all end? What's the ultimate fate?
Every story has an ending. Given the accelerating expansion driven by dark energy, the most likely scenario is what's called the Big Freeze, or heat death.
Sounds chilly.
It is. The universe just keeps expanding, accelerating. Galaxy clusters get pulled apart. Eventually, light from distant galaxies will be redshifted so much we won't be able to see them at all. A very lonely cosmos.
And stars.
Star formation will eventually stop. All the gas gets used up or spread too thin. Existing stars will burn out one by one, leaving behind cold remnants, white dwarfs, cooling to black dwarfs, neutron stars, black holes.
And the universe just gets colder and emptier.
Pretty much. Over truly unimaginable timescales, everything approaches absolute zero. No energy differences left to do any work. Just cold, dark, empty space expanding forever. A slow fade into nothingness.
Is that the only option? Zoran mentioned something more dramatic.
Ah, yes, the Big Rip. This is a more speculative, violent end. It depends on whether dark energy stays constant or actually gets stronger over time.
What happens if it gets stronger?
Its repulsive force could eventually overcome everything. First, it would pull galaxy clusters apart, then galaxies themselves, then solar systems' planets rift away from stars.
It keeps going.
In this scenario, yes. Eventually, it would overcome the electromagnetic force holding atoms together, and finally even the strong nuclear force holding nuclei together. Space-time itself would be torn apart.
Yikes. A messy end indeed.
Definitely not the gentle fate of the Big Freeze.
What about the old idea, the big crunch, everything collapsing back?
That was the favorite idea before dark energy was discovered. If there was enough matter and energy, gravity could eventually halt the expansion and pull everything back.
The Big Bang in reverse.
Essentially, yes. Everything rushing back together, getting hotter and denser, ending in a singularity. Some even theorized a big bounce, a new Big Bang emerging from the crunch. But with dark energy accelerating things, a crunch seems very unlikely now.
Okay, so probably a freeze, possibly a rip. What about the things left over in the freeze, like black holes?
Even they aren't forever. Stephen Hawking came up with Hawking radiation. Due to quantum effects near the event horizon, black holes actually leak energy very, very slowly.
They evaporate.
Over mind-boggling timescales, yes. A solar mass black hole might take 10 to the power of 67 years. But eventually, they should evaporate completely in a final flash of radiation. Even the ultimate prisons decay.
So in the far, far future of the big freeze, what's left? Just cold cinders and particles.
Maybe even less than that.
Eh.
There's a theoretical idea called proton decay. The standard model says protons are stable, but some more advanced theories, grand unified theories or GUTs, predict they might decay, just with an incredibly long half-life.
Longer than the age of the universe by far.
Oh, vastly longer, maybe 10 to the 34 years or more. But if it happens, eventually all ordinary matter would dissolve into lighter particles like positrons, neutrinos, and radiation.
Leaving?
An incredibly dilute, cold soup of fundamental particles spread essentially infinitely far apart. No structure, no heat, no light, just the final silence, the ultimate heat death.
It's hard to even wrap your head around that level of finality.
It truly is. The end of everything, stretched over timescales that make the current age of the universe seem like an instant.
Imagine you could somehow survive until then. The big freeze. Stars are gone, black holes have evaporated, maybe even protons are gone.
You're the last consciousness in an utterly empty, cold, dark, expanding void.
What would you even perceive? What memories would remain of the bright, bustling universe? What final thought would you have for the vast, silent emptiness?
A profound thought experiment.
Well, we certainly covered some ground today. From the Big Bang's first fractions of a second, through star birth and death, galaxy formation, the fundamental forces, the deep mysteries of dark matter and energy, all the way to the potential end of time itself.
It's been quite the journey through Zoran's chronicle, putting the universe's grand narrative into perspective. From fire and fury to, potentially, a cold, quiet end.
So the final thought for you, listening.
You've traveled with us through these immense timescales, from that explosive birth to a possible silent demise. If the cosmos might be heading towards a state where even atoms dissolve and time itself maybe loses meaning, how does that vast perspective change how you see your own life?
Does it make our fleeting, vibrant existence seem more precious? Or perhaps something else?
Something to ponder.
We hope this deep dive has sparked your curiosity. Keep looking up, keep asking questions. There are still so many mysteries waiting in the cosmos. Keep exploring.